All right, welcome back. It is good to see everybody here today. It turns out there's two fundamental problems in calculus. And if you can understand the solution to either of these problems, then you understand the fundamentals for either branch of calculus. The tangent problem is a classic problem that leads us to what's called the derivative, and in general, differential calculus solutions. The area problem is a problem that, if we can solve, gives us the foundation to work with what's called integral calculus. So today we're looking at what's called the tangent problem. We need to understand, and there's a lot of terminology here in this lesson, how the slope of what's called a secant line can be used to determine the equation of what we call a tangent line. And once we understand how that works, we're going to actually do that. So the first bullet here is just understanding, in a general sense, what the relationship between a secant slope and a tangent slope is, and then using a secant slope to determine a tangent slope. We've heard this word tangent before. In Math 30-1, and I know that not all of you have taken Math 30-1 yet, when we talk about a multiplicity for a polynomial function that's even, and what that means is that the polynomial function, if it has an even multiplicity at, say, this point, what it means is that the graph might come down and just touch that point. Do a better job than that. Just touch that point and then return from whence it came, back up. And we say that that's a tangent point. And by the way, tangent here for everybody has nothing to do with trigonometry. There is a connection. There's a reason why we use the word tangent here and tangent in trig, but it's not important. Tangent here is meaning something different, just kind of touching. The only thing I want to address to begin with here is don't get fooled into believing tangent points always have to be x-intercepts. They don't. It's the nature of the curve and the x-axis that allows us to say that the x-axis is tangent to the function there. We could say the function is tangent to the x-axis. We could say the x-axis is tangent to the function. They're tangent to each other. So if I asked you to draw a tangent to a circle at a particular point, specifically this point, you might draw that line. Okay? And that's kind of an intuitive approach. Notice that the line just touches the circle at only one point. And I think it's better to say it glances off of the circle. And the reason why it's tangent is because of that touching it at one point and glancing off of the circle. You want to be careful here, though, because if you get sucked into believing that a tangent line is tangent because it only touches the curve at one point, that's not always the case. Okay? By the way, the word tangent, I think it's Latin. It comes from the word tangere, which means to touch. But I've got two graphs here, and I'm talking about the point on the function where x equals 2. Let me highlight that point for us. I'm talking about this point here. And I think it's quite clear that the graph on the left has a line that's tangent to the curve at that point. Intuitively speaking, that makes sense. And when I take a look at the line on the right, I hope you would agree that the line on the right is not tangent to the function at x equals 2. And yet, the one on the right passes the test for, well, it only touches the graph once, right? Over here, the one on the left touches the graph in more than one place, but it is in fact tangent. Whereas the one on the right does in fact touch the graph in only one place, yet it is not tangent. So it turns out that the definition of a tangent line has to do with how a secant line behaves close to the point of tangency. And that's what this lesson is all about. But, and this is so subtle, you might read this and go, man, he has just typed out the same thing twice. I haven't. The slope of a tangent line to the function at x equals some number. The slope of the line is the same as the slope of the function. at that point. There are two different slopes we're talking about here. We're talking about the slope of the line that's tangent to the function, and we're talking about the slope of the function at that point. And the issue is, in junior high and senior high math, the concept of slope is typically only defined for a straight line. But if we can use this idea, then we can not worry about the curve and instead find the slope of a line and say it's the same as the slope of the tangent, which means it's the same as the slope of the function. That, like I said, that's subtle. We sometimes call this the instantaneous slope of the function at x equals a. I don't know if any of you remember this from Physics 20, but you might have taken a Physics 20 course where you graphed a function that showed distance as a function of time, and you had to find the speed at different points by drawing tangent lines. That's what we're talking about. You know, more specifically, to drive home the point that's at the top of the page, if we go back to this diagram, and I told you that that line has a slope of 6 over 7. Ignore the curve. I'm telling you, I determined the slope of that line, and it happens to be 6 over 7, which is just a made-up thing. Then what that means is 6 over 7 is also the slope of the function at that point. I hope everybody understands, I cannot say this function has a slope. I cannot say this function, by function I mean this, I cannot say that this function has a singular slope, because it doesn't. Its slope is always moving around from different value to different value. But what I can say is, again, at the risk of being overly repetitive, at x equals 2, the slope of that function is the same as the slope of the tangent. So when I kind of, I don't want to say glibly, that's the wrong word, but when I kind of raced through this at the beginning on day one, and I said, if this was a function of mice compared to days, and I had these 3 days, I just kind of, and it was glib, I just said, well, what if the slope of that line is 25 mice per day? Rise as mice, run as days. Then what I said was, if the slope of that line is 25 mice per day, then the mouse population at that instant is increasing at 25 mice per day, right? Remember that? But when I say that, I'm no longer talking about this line, I'm talking about the curve. Right? I use the line to tell me what the curve is doing at that point. I think you're getting the idea. If the slope of this line is 8 mice per day, then the graph that's in red has a slope at that instant of 8 mice per day. By the way, I haven't explained why the slope of the tangent is the slope of the function, but I think intuitively it's the case. However, there's this kind of, I don't know, analogy, I don't know what I want to call it, this thing that I've come up with where you're in a car and it's very foggy and your headlights are on and you're driving up and down this mountainous hill. If you've ever driven in the fog with your headlights on, you know that your headlights form a beam of light there. That slope of that beam of light is the slope of the road that I'm on. And that line, that beam of light, is tangent, I didn't do a perfect job there, is tangent at that point. But I don't think we need to get into a proof as to why those slopes are equal. And of course, if the slope is negative, then the rate of change of mice with respect to time is negative. So we have a bit of a warm-up here. I know it's example 1, but it is really a warm-up to the main show. 2 tangent lines to a function are shown below. Can you make sure that you have a tangent line at 20 for x and at 60? Because I had 2 different sets of problems at one time. Okay, good. So determine the slope of the tangent at each point and interpret your answers. The graph is showing the cooling of a pot of spaghetti. I hope you know, based on these blue lines that we're going to find the slope of, and based on the grid we're dealing with, we're going to be doing a little bit of estimating here to read data points. Okay? I do, in fact, want to use data points that are easy to read, or easier to read. So for the 20, in other words, for this one, let me get a highlight on here. And I don't think you necessarily want to muddy up your diagram with a whole bunch of arrows and stuff. I'm going to be using this point here. Now I know looking at it, it's not at exactly 10, 60, but that's as good as it's going to get here. If you want to say that it's at 10, 59.5, have at her. I'm going to say that point is at 10 minutes, 60 degrees Celsius. So what's happened is somebody's heated up some spaghetti sauce, they've turned the burner off, and it's going to be cooling. Of course, if you've taken Math 30, you will know that there will be an asymptote here, a horizontal asymptote, which will be room temperature. And I'm going to use, I don't know, I think I would like to use this end point. It's somewhere between 30 and 40. I would say, judging it, it's 6/10 of the way. I would say it's 36. And then I can use those data points. So the point on the left is at 10, 60. That's one of the points on that line whose slope we're after. The point on the right is at 36, 20. I want to step back and just double check that. 10, 60, 36. Yeah. If you went 35, I wouldn't quibble, but 36, 20. So now what is my slope of, well, I was going to write what is the slope of the line that's tangent at 20. But what I'm actually going to write is what is the slope at 20 minutes. Because the slope of that line that's tangent at 20 minutes to the function will be the slope of the function at 20 minutes. Right? And I know that's repetitive, but I want it to sink in. So that's simply going to be y minus y over x minus x. I kind of just at this point wish I would have said 35. Would have come up with some nicer numbers, but that's okay. Y minus y over x minus x. And I've made a mistake here. What is the mistake? And it's an important one. It's important that you do not make the mistake, Jay.
The graph's going down, so we should have a negative.
I should have a negative, and the reason I'm not getting it is I went 60 minus 20, and then I went 36 minus 10. I should be subtracting in the same order. So if I take this top y coordinate minus the bottom y coordinate, I have to take the top x coordinate minus the bottom x coordinate. So I'm getting 40. This is for the 20-minute one. I'm getting 40 over negative 26, which is 20 over negative 13, which I couldn't tell you. We do want a decimal number here. I don't think it creates anything of value for us to write that the slope is negative 20/13, or whatever it is. Okay? So what do we have? We have 40 divided by negative 26. I'm getting negative 1.5 to the nearest tenth, which I would say is a reasonable place to round. So what does that mean? Well, I just had this conversation with my Math 30-3s, and we've been having this conversation since the beginning of the semester. You can't interpret a slope unless you include units, right? This is not just, 60 minus 20 banana daiquiris or monkeys. It's 60 minus 20 degrees Celsius. And this is not 10 minus 36, it's 10 minus 36 minutes. So what we're getting is degrees Celsius per minute. And what it means, and you got to wrap your head around this somehow, is that the temperature of the pot of spaghetti sauce at that instant in time, at an instant in time, is decreasing at 1.5 degrees Celsius per minute. But the units are in reference to a whole minute, but it's at an instant in time. And I believe I've talked about this before. Just because you happen to look at my speedometer and it says 120 kilometers per hour does not mean that I'm traveling for an hour. I might only be traveling at 120 kilometers per hour for an instant, which is why this is called an instantaneous rate of change of the function. If we do the next one, I'm just going to go with the end, and we're going to do our best to read these as well as we can. I mean, we're not landing people on Mars here, right? It doesn't have to be perfect. I'm going to go with both endpoints. What the heck? So my slope at the 60-minute mark will be equal to y minus y. This time I'm going to go this y coordinate here, and I'm going to say that that is pretty much 15 minutes, minus this y coordinate, which I'm going to say is 24 minutes, although I would think that you might say 23 there. I don't know. I hope you catch my drift here, that I'm talking about this being 15 and this being, now that I draw it, it doesn't look like 24. What do you want to go with? Oh, no. Oh, okay, good. What do you want to go with there for that? 23? Okay. I'm convinced. And then on the bottom, we have to go x minus x. Of course, we want to subtract in the same order for the x's as we did for the y's. So I'm looking here now at this. I'm going to go 96. And if you want to go 97 or 95, 97, I don't care. All right, that's not the point. And then over here, I'd probably go 38. Yeah. We're still going to get a negative. It will still be degrees Celsius per minute. But, and you can tell by looking at that second tangent line, it is not as steep. And if you've ever done any kind of cooking or managed to survive in the real world dealing with hot objects, you will understand that when they're very hot to begin with, they radiate energy very quickly. And then they tend to settle down very close to a low temperature for a long time. Alex, can you help me out here and tell us what you get to, I'm going to go to 2 decimals.
Negative 0.14.
0.14. Is anybody else okay with that? No, you're all alone there, Alex. I'm just kidding. They're giving me the thumbs up. So what it means is at that point in time, the rate of change of the temperature of the spaghetti sauce with respect to time is negative 0.14. These are important things. I mean, I forgot my C for Celsius. They're not like glaringly important in the world that we understand the rate of change of temperature change relative to time for spaghetti sauce. But this is a scientific thing, right? Maybe instead you're talking about the rate of cooling of a rocket engine as it ascends into the atmosphere. Could be all kinds of scientific applications. Any questions with that first example? All right. So, example 2, and this is it. This is the tangent problem now. And I'm approaching it with you for a particular function. And this is what this sheet is I've given you. At the top of page 8, the top right-hand side of page 8, you have a diagram that you're looking at up here right now. But it is pretty tiny, and for what I'm going to ask us to draw on here, I think you need a bigger sheet. So I'm not sure why I made it so small in your handout. Consider the problem of trying to find the equation of the tangent line to this function, y equals x squared, which everybody should be intimately familiar with. It's a parabola that opens upwards with its vertex at the origin. It goes through 1, 1, 2, 4, 3, 9. It's pretty basic stuff. And I've drawn a tangent line, and it is tangent at that point 3/4 for x. And you can put 3/4 in here if you like. I would say the less you draw in this diagram, the better. I would just say that you should know that if this is 1 and this is 0, then each of those squares is a quarter. So that x coordinate is at x equals 3/4. Now what we want to find is the equation of that line that's tangent at that point. Okay, it's a straight line. Why do we want to find that? Because the slope of that line will be the slope of the function at that point. And we need to know how to do this. What is it we need to know to find the equation of a line? Well, you need to know the coordinates of a point on the line. This goes back to Friday. And you need to know the slope. Okay, so this is the problem. Finding the coordinates is easy. Finding the slope is the calculus part. Well, if we talk about the coordinates of the point, that point that's on the tangent line whose equation we're trying to find, that point has an x coordinate of 3/4, but it's also a point on the function y equals x squared. So finding the y coordinate of that point is really simple. Right? It's a point on the line, but it's a point on the function. And the equation of the function is f of x equals x squared. So all we have to do is put 3/4 in for x into y equals x squared. I'm not even writing this. And when we square 3/4, we get 9/16. So we have those coordinates. That's the coordinate pair, or ordered pair, of that point, which is on the tangent line. Now, we use the fact that it's on the function to find the coordinates, but it's on the tangent line. And we need to label it on the diagram, and my recommendation is to label it someplace over here. There's going to be an awful lot in this diagram. And if you put it someplace else, you might be putting it somewhere where we're going to need to write something else. All right, well, what else do we need to know? We need to know the slope of the tangent. So we're going to go through an exercise here which may seem to you like we've lost the thread of what's going on. We haven't. We're going to talk about something different now. Complete the table to the right and plot the points on the graph. So I'm asking us to find the y coordinate when x is 3 and x is 2.5 and 2 and 1.5 and 1 and 0.8. Why these numbers? Because I've chosen them knowing that it's going to be useful. And don't worry about plotting them just yet. Let's find the coordinates. 3 squared is 9. 2.5 is 5/2, right? I actually had a student many years ago, and I still to this day don't know if they were serious. Correct? I think they were pulling my leg, and I think they kept up the ruse all semester. I have to believe they knew that that wasn't the case, okay? It's 2.5, it's 5/2 because that's what 5 divided by 2 is. It's not because there's a 2 and a 5. So 5/2 squared is 25/4. That happens to be 6.25. 2 squared is 4. 1.5 squared is 2.25. 1 squared is 1. 0.8 squared is 0.64. So we have to plot these points, but we're not going to label them, in terms of ordered pairs. I'm not going to write 3,9 on the grid and 2,4. I'm just going to plot the points. And plotting the points is easy. If I want to plot the point 3,9, I just have to put a point where x equals 3 on the function, and it's going to be at 9, right? If I want to plot the point 2.5 was the next one, I don't even care what the square of 2.5 is. If I go over to 2.5 on this grid and plot the point, it's going to be at, was it 6.25? Okay. The next one was 2, so I plot at 2, and it's going to be at 4. Now, some of the points may not appear perfect because this graph I've constructed using Word and Excel, and there's some rounding going on, so it's not a perfect parabola. I think 1.5 was the next one, 1 was the next one, and then we have 0.8. which is very close to 0.75. And this is maybe going to be the point, one of the biggest points, no pun intended, is that this last point is getting annoyingly close to the point that we care about finding the slope of the tangent to. So we've got that. Part C. A line that connects point P and another point on the curve is called a secant line, okay? So, in this table, these are just coordinates, and this is just point Q1, Q2, Q3, Q4, Q5, Q6. Be very careful with this table. This table is not talking about a point. This table is talking about a secant line. And this secant line, PQ1, is the line that goes through the point P, which we care about, and the point Q1, which we don't care about. Of all of these points, everybody, the only one we really care about is this point P. All of these other Q's are going to be used in a certain way, but we don't particularly care about them. So, this is the line whose slope we want to find, right? And we call that a tangent line because it is, quote, just glancing off of the function. This line is not a line whose slope we care about. And some of you might go, well, so why do we draw it? Hang on, some of you may have started to figure out where this is going. This line is called a secant line. And I think it's quite obvious that the slope of that secant line is not the slope of the tangent line that we care about. Yeah? They have different slopes. So just so you're interested, if you're interested, secant comes from Latin secare, which means to cut. So secant line, and don't worry about how it connects to trig. You know, secant, cotangent. Don't worry about it. So that's a secant line connecting point P and Q1. This is a secant line approaching, connecting P and Q2. You with me? This is a secant line connecting P to Q3, P to Q4, P to Q5, P to Q6. So I've drawn in a line here very delicately that goes through the blue point, which is point P, and the red point right next to it, which is Q6. What I want us to do is find the slope of all of these secants. Now, I want you to follow along carefully so that later on, when we learn the slicker ways to do things, it will start to fall together. You know, you certainly could do this. Don't write anything. You certainly could say that P is at 3/4, comma, 9/16, and Q1 is at 3, 9, right? And then you would go 9 minus 9/16 over 3 minus 1/4. Sorry, 3 minus 3/4. Are you with me on that? Okay, I don't want you to do this. I don't want you to calculate anything. I don't want you to write anything. But then what you would do after doing that is you would say, well, okay, I'm going to move on to Q2. In Q2, am I using Roman numerals? Okay. Was at 5/2, comma, 25/4. Am I right? Look at your data table. Yeah? So then you would put 25/4 minus 9/16 over 5/2 minus 3/4. But here's my point. When you look at calculating the slope of secant line PQ1, you have 9 minus 9/16 over 3 minus 3/4, where 3 and 9 are the coordinates of Q1. The only thing that changes when we go to Q2 are these two numbers. It's still minus the y-coordinate of the point of interest over minus the y-coordinate or the x-coordinate of the point of interest. So what I'm saying is, why don't we say that the slope of the secant line is equal to the y-coordinate on the function minus 9/16 over the x-coordinate on the function minus 3/4. Are you with me? We've come up with a general formula, and we're going to make it even more useful. Because I don't need to put the y-coordinate in here. I can put x squared. So what I've created is the y-coordinate of point Q, which, listen carefully, is a mobile point. It's a point that's moving closer to point P. It's moving all over the place. We can move it wherever we want, except we can't put it right on P, because you can't find the slope of 2 points that are on top of each other. So the y-coordinate of the mobile point, which is the value of the function, minus the y-coordinate of our point of interest, over the x-coordinate of the mobile point, minus the x-coordinate of our point of interest. Why don't we just put this in for y1? We're not graphing anything here. And just go to our table and put in the different x-coordinates for all of these points and read what the slopes of the secants are. Are you with me? You don't have to do it that way. You could do what I suggested over here. Right? You could do this for the first point and then repeat it again for the second and repeat it for the third. But I want you to see what I've written here. It's important that you see that, okay? For a reason I'm going to reveal in a minute or two. Or maybe not till tomorrow. I always never decide, okay? So I'm going to put in for y, and this is not y, right? It's just a way for me to enter that expression to evaluate that. This is a function of x that's going to calculate the secant slope. So I'm going to put in brackets x squared minus 9/16 divided by, in brackets, x minus 3/4. And I'm going to set up my table so that I am allowed to enter any value of x. And if you're really following along, you will realize then that we really didn't need to find, that we really didn't need to find, I went the wrong way, going the wrong way, there we go. I'm getting there. We really didn't need to calculate these numbers, did we? Because we don't care what they are, we care what x squared is, minus that y coordinate. So let me get back to where I want to be. There we go. So I'm going to set up my table, which will allow me to independently put in numbers for x. And I'm going to put in 3. Well, this is the slope of the secant line. I'm going to put in 2.5. I'm going to put in 2. I think the next was 1.5, then 1, then 0.8. It's just, you have this graphing calculator, why don't we use it? We're not graphing anything. What we're doing is we're determining, using tables and an equation for the secant slope, we're determining the slopes of all of the secants. So what do we get? We get these slopes. Are you still with me? And now I know why I made the diagram so small, and this isn't a criticism. Nobody ever draws all of the secant slopes, because I think you're picking up the idea here. You're going to pick it up without drawing it. But if you want to draw them all, you could. Maybe it's a good idea that you just follow along up here. Don't worry about that. This secant line from P to Q1 has a slope of 3.75. Would you agree that the slope of that secant line is different than the slope of the tangent line? Glaringly obvious, right? Way, way too big. But we've discovered that the slope of the next secant line is 3.25. Would you agree that the slope of that secant line is really mathematically nowhere near the slope of the tangent line? But would you agree it's better? It's closer to the slope of the secant line, or to the slope of the tangent line, rather. 2.75. Well, the slope of the black line, which is a secant line, is not the same as the tangent line, which is brown. But it's closer. And in fact, as we get closer, there's the slope of secant line PQ5. If we go to PQ6, and that's difficult to draw, and you actually look at the secant line, which is in black, whose slope is 1.55, and you look at the tangent line, whose slope we want to find, in the words of my grandpa, pert near the same. By the way, it took me years to understand that what he was saying was pretty near. Pert near the same. They're almost the same. So at this point in time, could I make a conjecture and say, I think the slope of the tangent line is around 1.55? Yes. But that's not good enough. Okay? The slope of any of the PQ secant lines will always be unequal to the slope of the tangent line. What's the relationship between the slope of PQ and the slope of the tangent as Q approaches P? And this is a way for me to introduce important notation. As Q approaches P, and it has to be Q approaching P. P doesn't approach anything. P is a fixed point. Q is on the move. As Q approaches P, the slope of the secant approaches the slope of the tangent. But there's a better way to write that. The better way to write it is to say this. Why not get specific? Why not say that the only way Q can be getting closer to P is if the x-coordinate on Q is getting closer to 3/4? Because 3/4 is the x-coordinate of P. In fact, if you take a look at these diagrams I've given you, what's happening is there is some value of x here that these red points are all getting closer to by moving to the left. 3 for x is not really that close to 3/4, but 2.5 is closer, and 2 is closer, and 1.5 is closer. In fact, is there any limit to how close we can move Q to P? No. It's just that, do you agree, I'm going to throw this out, I've made my decision on which way to go here. Do you agree that when I say x is approaching 3/4, x cannot be 3/4? Why? Well, because the slope of the secant is equal to x squared minus 9/16 over x minus 3/4. So mathematically, if x is 3/4, then you're dividing by 0. And that makes sense because you cannot calculate a slope with rise over run when the 2 points are on top of each other. I'm going to come back to that in a little bit. So I've got this written here in a different way. I don't know why. I really like what I have written here. Specifically, well, they're both great. They're both very important. This, but to be a little more specific, this. use this idea to find the slope of the tangent. Well, this is why I asked us to set this up. Is 0.8 close to 0.75? Yes. So the slope of the secant at 0.8 to p is pretty close to the slope of the tangent. But I can get even closer. And as we get closer, that slope of the secant gets closer to the slope of the tangent. So I can put in 0.78, which is really, really close to 0.75. I can put in 0.751. And by the way, if you want to see more decimals on the output, scroll over and highlight it. I can put in 0.75001. Now when I do that, it's probably going to say 1.5, but it's not 1.5. Okay, it's not 1.5, but it's getting really close to 1.5. And I hope you understand or trust me that if I go 0.75000000000001, that this is going to say 1.5, and it will probably say 1.5 here because my calculator will round it to 1.5. But it's not exactly 1.5. What do we conclude? The slope of the tangent must be 1.5. It's an intuitive thing, right? I would write the answer here. It appears that as x approaches 3/4, the slope of the secant approaches 3/2, 1.5. But we know that the slope of the secant is approaching the slope of the tangent. So the conclusion is that the slope of the tangent is 3/2. Now there's more to this. There's a lot more to this. Okay, and I'm going to reveal certain aspects of the a lot more in a few minutes. But let's finish the question. The question originally was, what is the equation of the tangent? So all we've determined is the slope, but now we know the point passes through 3/4. It's been a very long day for me. I'm not really feeling myself. Is that right? And the slope is 3/4, no, 3/2. So y minus y1 equals m x minus x1. And, you know, of everything we're doing today, this is the least important thing. It really is. We're just going through some Math 10 now. There's a lot of fractions, so it's a little more complex. We're going to have y minus 9/16 equals the slope, which is 3/2, times x minus 3/4. Let's talk about some basic math here. If you decide that you're going to multiply both sides by 16, you will, don't write this, if you decide to multiply both sides by 16, you're going to get that. Okay? 16 times y is 16y. 16 over 16 is 1, so you're left with minus 9. 3/2 times 16 is, well, 16 over 2 is 8, times 3 is 24. And then you have the x minus 3/4. I'm saying why bother to do that? Because now you have to expand this out, and then you're going to have to get rid of more fractions. Why not expand the whole thing out and get rid of the fractions in one fell swoop? I don't care. It's just a piece of advice. So I would multiply this out. Y minus 9/16 equals 3/2 x minus 9/8. It turns out that multiplying everything by 16 is going to work, and this time it's going to get rid of everything in terms of denominators. Can you check my arithmetic there? Good. So multiply everything by 16. I know you're not supposed to do this, but it's just us in the room. Nobody's watching what we're doing. You should be going left side times 16, right side. I get 16y minus 9 equals 16 over 2 is 8 times the 3x. 16 over 8 is 2 times the negative 9. So 0 equals 24x. Sorry, can you check my arithmetic again? I'm pretty sure it's right, but this pounding headache. Minus 16y minus 9 equals 0. And we're done, okay? But maybe I will review what we did here. When you're doing the problems that I'm going to assign today, what you are doing is you are picking a point. Well, there's a point P, which is the slope, or the point where you want to find the slope of the tangent, okay? And what you do is you pick a point close to that point, and you call it Q. And you find the slope of the secant, and then you move Q closer to P, and you find the slope of the secant, and you continue to do that, and then you reason out what it would be. Your textbook for these problems gives you recommended choices for where Q is. But I don't care how you do it. In fact, I'm going to show you a shortcut here in just a second. Once you figure out what that slope of the tangent is, because you're saying as x approaches this number that's the x coordinate of point P, the slope of the secant will be what we're after, or it will approach what we're after. Then you find the equation of the line. But I want to go back to this here. Because I've said that as x approaches 3/4, this approaches what we want to find. Yes? Why can't I just put 3/4 in? We've discussed that already. Because then you'll be dividing by 0. And from a practical standpoint, you will have P and Q in the same location. You can't do that. You can't find a slope that way. So we can't put in 3/4, but I would like you to put 3/4 in the top and the bottom and figure out what you get. Well, you get 0 over 0, don't you? There's a reason for that. The reason for that is the rise from P to Q when they're on top of each other is nothing. There is no rise. And the run from P to Q, there's no run, right? So you can't put in 3/4. But what if we cleaned this up? What if I said, you know what, I'm going to multiply top and bottom by 16. Now, by the way, we use 16 in the equation as well, and I don't believe it's a coincidence. There's 16s involved in this. But I do that. I'm just playing around with this, and I get 16x squared minus 9 over 16x minus what I believe is 12. Can you double check my multiplication there? Oh, I got a difference of squares on the top. And it factors into 4x minus 3 and 4x plus 3. And the denominator has a factor of 4, which leaves 4x minus 3. And there's something about this, and I'm not kidding, that I find spooky. Any function when you do what we've done, you will always, no matter what point you choose, you could choose a point out at 1,000 or negative pi, any point, everything will always be factorable or clean upable so that this goes away. Do you agree that the obstacle to putting 3/4 in is that factor? Well, now that factor is not there. It's like we're finding the y-coordinate of a hole, but what you're finding is the slope of the tangent. Because if I put 3/4 in to whatever's left, I get 3 plus 3 over 4. You do not have to make a table of values and find the slope of the secant and then nudge point Q a little closer and find the slope of the secant. You can do it this way. But you do need to understand what's happening, that it's a slope of a secant approaching the tangent slope. And it doesn't matter. You could take, let me show you. Let's say we have the function y equals 2x squared plus 3x minus 1, and we have a point. Give me an x coordinate that's not crazy. 4. Calculate the y coordinate. I'm not trying to rush you. I'm just saying everybody calculate the y coordinate. I'm getting that, but yeah? So this is point P, and I'm doing this to show you how you're going to do your homework assignment. This is point P. It's fixed. It's at 4, 43. What is Q at? Well, Q is a variable or mobile point. It has an x coordinate that's always on the move. And what is the y coordinate of Q? It's that. What I'm telling you is that this minus 43 is always going to be factorable. It didn't matter what number you picked. If that doesn't bother you a little bit, then maybe I'm alone here on this, but that really, my slope of the secant, this really bothers me, will be y minus y over x minus 4. I'm interested in knowing at x equals 4, and I can't do it. I can't, right? Go ahead and put 4 up here. You should know you're going to get 0 because this is 43, right? But that means, I think this is wild. Is that without even thinking about it, I know that has a factor of x minus 4. It has to, because the slope of the tangent exists there. So there's got to be an x minus 4. It better be 2x. Well, you're going to have to figure out where to put the positives and negatives. I'm thinking that's right. So put 4 in and get help 19. Okay. I could have told you it was 19 and 1/5 the time without doing this at all, and you will learn that later. One final thing. What I'm about to show you is not really anything you can use on an exam because I'm showing it to you. So I'm going to graph y is equal to 2x squared plus 3x minus 1, I think. Yep. And I'm going to set up my window settings to go from (0 to 6 for x and 0 to 100 for y. And there is the function. You said at x equals 4. Okay, if I go to my calculate window, that looks suspiciously like a formula for slope. It's not, because this isn't a slope of a secant line. This is the instantaneous slope, and I enter 4, and I get 19. If you want to, you can go to calculate. No. You can go to draw tangent and enter 4, and it will draw the tangent, and to boot, it will give you the equation of the line. Okay. These are things you can use to check your work. They're not how you would do an exam question. So, for these questions, everybody, 7, 8, 9, 10, I don't care how you find the equation of the tangent curve to the function at that point, as long as it's done on paper. I don't want you to find it using your graphing calculator like I just showed you. Any comments or questions about any of that? There will come a time where you will be able to determine an equation for the slope of the tangent. Go ahead, put 4 in here. What do you get? 19. Put 3 in there. 15. Okay, so things will get easier and then they will get more difficult. Anyway, you can see what the assignment is. I don't care how you find the equations. I want you to find them algebraically on paper.